My name's Jake. So recently I started applying for a bunch of positions at JPL as an intern, and then one of them accepted me, so I signed up for school and went. Was not actually in school when I signed up. And then, so at first I told them I had shop experience, so I was putting together opening boxes, and then she found out I could learn software, so I decided to start doing CAD modeling. So then I was CAD modeling for 8 hours a day, wondering, is there a better way to make this part? I'm just guessing. I don't have a mechanical engineering background, so I'm like, what's the most efficient way to make this bracket, this part? Just kind of guessing. So I found out there's this thing called shape optimization. Some people call it topology optimization, and if you don't know what it is and you've seen pictures of it, you call it that crazy bone-looking thing, and you'll know in a second. So CAD modeling, computer-aided design, I'm sure you've all interfaced with it or need to know about it. But shape optimization is where the computer designs the most efficient shape structure for you automatically, and you just clean it up at the end. So I don't know, computer-aided design? I don't really know what you'd call it, but so when you go to start a project, you ask yourself, what's the best way to make this? Depends on the situation. Is it the cheapest? Is it the lightest? Is it the strongest? Is it the most environmentally friendly? Least over-engineered? And also, does it meet the requirements? So like, what is best is basically changes based on what you're doing. So here's the design challenge. So this is a bearing up here. Imagine it has 100 newtons of downward force and 2,500 newtons of axial thrust load, and then these are 4 fixed positions. So if you were me, I would probably just do something like this. It seems pretty obvious. You make like a bracket, holds the 4 bolts go in, and then you have this because there's the downward force, so that's super strong looking, and then this beam out the back. Seems pretty obvious. You could probably weld that, you could CNC machine that. There's a couple ways to make that. Wouldn't take too long to CAD, but if you ask a computer how to make it, they actually end up giving you something like this. So, to be honest, I actually didn't have the downward axial thrust. I only had the forward and back, and that's what Fusion 360 said. There's also a slider, so like the gray box is the build area. So you say you can use anything in this space to create a strong shape, and then it decided that the green. I wish the slider was here because it would turn on. It goes yellow, red, bright red, and at the core there's this bright red little husk. So this is a program here this one's free and this one's $150 a month. But you end up with this kind of, it's not super smooth, but it has like a hole here and it has this little foot and this little thing. You'd never think of all these things. And so you take that shape and then you work with that in CAD. And interestingly enough, if you see my mouse, cool. So see this like foot here? If you delete this foot, this part has to connect to here because it will roll backwards. And there's two ways really to optimize. You can optimize for weight reduction or stiffness. So this is weight reduction. So this foot stops that center beam from rolling and stops you from having to have 2 beams, one going to each of the bolt points. Ends up being a way stronger way to make it. So this is, try not to be too boring here, but normally when you're designing things for like aerospace, for example, the cost to launch something is almost the cost of its weight in gold. So like if you save an ounce, like you're saving a couple $1,000s. So weight savings is super important, and if you're like a Boeing or airplane company, you can save a pound. You know how many times the plane can fly before its life is over. And you know how much fuel you'll save having 1 less pound on every single flight. So you can calculate the value of having 1 less pound in your entire thing. And if the development cost is super high and the manufacturing cost is super high, it might not even matter because you can definitively say it's going to save you money. So you end up with these kind of long processes for making parts, where first you say, it needs to be able to do this, have this quality, have this cost. And then you kind of, if you're clever, you come up with a layout, a shape, an idea, it's your concept of how to make this part. And then you decide, what are the tolerances? Does it really have to be that accurate? How do you plan to make that? And then you make one, and then you test it, and if it doesn't work, you change it, you know, if it's possible, and then generally someone comes in and says, this is too expensive. You have to make this out of plastic instead, so then you have to go back to the concept design, and then you're back over here, and you're realizing it's a different material, which means a different manufacturing process, and so you go through this until eventually it works. So shape optimization, what's interesting is it actually saves a ton of time. So in the performance here, I have a 100 kilogram load going downwards on this hook. So you know the cost, quality, performance, accuracy, layout, shape. You run a simulation in your concept. Since you already know the requirements, you can enter the requirements into the computer and it'll generate the shape. So you define the maximum available design space. Sometimes it'll come up with a shape you never would have thought of. So it's important to make this big if you can afford for it to be big. Dimensional tolerances. So what I probably would have done was made this beam the same height as all of this plane and the same height, so you could have just like water jet or plasma cut it out of a flat piece of stock. But knowing to have a beam here and a beam here and a beam here, I never would have guessed that. And so the programs that make these objects, they generally also test the objects. So you put your cleaned up shape optimized part into the simulation. It tells you this beam's thin here and this beam's too thick. Red is where the forces are, and this comes back later. You have this kind of loop later on where you shape optimize, clean up, and then you rerun the experiment again. So some examples. So these are like formula SAE. They're like students in engineering schools make these go-kart things. What's really cool about the sport is almost all the engineers have all these new ideas. None of them are like entrenched race car builders. So they come with crazy ideas. And the sport's about engineering, not really about winning. So the rules on, the rules are basically you win if your car is the best engineered. So there's very few limitations on engineering. Like if you look at F1, the rule book is like ridiculous. You can't be too, there's so many rules. It massively limits innovation. But they were able to reduce part count, optimize weight, all these different things. You can kind of see this crazy front steering knuckle they made. So this is, it's actually happened a while ago, it was first 3D printed bike. But this part here, they weren't sure how to make it, so they used shaped optimization to come up with this ideal part here. So this is probably one of the most famous examples. There's an ESA Sentinel Sat-1. So this thing holds an antenna. And so they ended up getting 43% weight reduction. And so this is first modal frequencies. I didn't know about this until I joined JPL, but apparently they bolt your stuff to these like giant vibrator machines, and then they like harmonize. And if it harmonizes or it vibrates at too low of a frequency, it can like fall apart. So like, imagine if you had like a stiff rod like of steel with a bowling ball on it. Like if you shook it, it would shake it like maybe like 1 bounce a second. But if you added like support braces, then you shake it, it would vibrate quickly because there's all this support to it. And imagine if you kept adding so many supports that like you'd have to hit it with a wrench and it would go like ding. Like it's vibrating so fast, it's producing an audio sound. So stiffer stuff vibrates at higher frequencies, like less stiff things vibrate lower frequencies. So this is one of the requirements. But anyway, the important thing to notice here is that they ran the analysis on the part afterwards. They actually printed 2 of these and did full testing, but you can see some parts have red, and then I think they're showing here cross member could be discarded. And if you look here, there is no cross member. They ended up removing it. And then here, there's this big flat thing. They just decided that all this blue means it's doing nothing. So if you look here now, it's just a couple X's in the back. So you can continually go through the cycle of iterating and iterating. So here's another really cool challenge. So let's see. Reduce the bracket. Okay, let's see. It's weird because it shows me the next slide too. So optimize the bracket for minimum mass given the following performance requirements. 1G sag displacement, no further than I think 10 thousandths. First modal mode, 250 hertz. Original bracket performance. So this is what they had made, and they don't show pictures of this. Also, most of these slides, I ended up just snipping tooled them from a bunch of other slides on this topic that I liked. So if you do want more information, there's a lot more information on this I could give you too. But so these are basically the requirements. So when you work in the program, so this small box is hard to see. This is actually a mass. You define its mass, and then you just connect it to these gray points, and then that's like the part this bracket is holding. And then these arrows are where the part is fixed, mounted to another object. And then you run the experiment, and it gives you this kind of crazy thing. So depending on the input, you can input a different weight. You can input a different amount you'd like to reduce the weight by. And this person ran the experiment the first time and went, wow, this is way too bulky. Let's make it more spindly and thin. Ran it again and ended up being something that would take a long time to CAD model and a little bit too chaotic. And then came up with a third option, which is really good down the middle. Modern tools that do this just have a slider. So if it came out too bulky, you just slide it down and it looks great. And then they smoothed it, which basically means you made it a solid STL or a solid part that you can kind of work with. So you can kind of see this gray option here. This person just imported this into a normal CAD tool. So they completely made the part. It ends up kind of looking like this, actually. But if you can see these red surfaces, he inputted these as connecting to the mass, and that these 4 points are connecting to the surface. Then he measured at what's the highest frequency it starts to shake at, where the stress lines are, how much sag under 1G of gravity. And it ended up being a lot less, like 35% less weight. Ended up being a way better part. But is there a better way to do this? There totally is a way better way to do this. And that's using polyNURBS and like different NURBS tools. So this looks pretty crazy to me. I mean, this doesn't even look like a CAD model part you'd ever see. This totally looks like a piece of organic, like human bone structure. It's like we've evolved for millions of years to have our bodies be this specific way. And why do tree limbs taper at that exact amount? It's because the trees that didn't do that broke more often. Our bodies have harmonized with the perfect balance of not being too bulky, not being too spindly, not being too heavy, not being too light. And it ends up looking something like that. Not like normal traditional things like this truss that were designed to be manufactured easily. But thanks to metal 3D printing, making this costs the exact same, if not less, than printing the bulky, flat, squared off version of stuff. It's actually just as easy. So I think this will work, right? If I click this link.
Let's allow it.
Oh, sorry. Oh, that's not on this screen. Okay.